So I want to first attack a really simple elastic collision between two masses in one dimension. So I have m going this way at big V, and I have little m going this way at little v. And in general, what must be true? Well, I must have that m v vector plus little m v vector initial is equal to m v final plus little m v final, whether I have an elastic collision or not. Okay, that's momentum conservation in the collision. So momentum conserved. But I'm going to work in one dimension alone. So I will have, by the time I project everything onto the positive x direction, I will have mvi plus mvi is equal to, so maybe actually I'm going to reverse this so it goes that way slow so I don't have any issues. mv final plus mv final. That's a statement of conservation of momentum. But if the collision is also elastic, if it conserves kinetic energy, which is to say it's an elastic collision, then the initial kinetic energy, why am I reversing my order? 1/2 m v initial squared plus 1/2 little m v initial squared must be equal to the same sum on the afterwards, after the collision. So I'm going to treat the incident, the initial momenta, the initial velocities here and here as given. I now have two equations, and so in principle, I can solve for the final state. And the way I want to do that is by putting the terms that refer to the same particle on the same side of the equal sign. So with your permission, I'm going to multiply the bottom equation by 2 and rearrange a little bit. So we'll have v squared initial minus v squared final is equal to little m v squared final minus v squared initial. And I'm going to do the same thing. So this is the kinetic energy equation, number 2. And I also have a momentum equation, number 1, that I'm going to subject to the same treatment. I'm going to put the terms that refer to big M on the left. So that would look like VI minus VF. And I'm going to put the terms that refer to the little m on the right, and what would that give me? VF minus so that's just rewriting equation 1. Now, is there any way to simplify? you should, at this point, be having a Pavlovian response, which means you're salivating, you see an algebraic expression, and you have this urge to do what? To recall, because your algebra teacher told you that the difference between two squares can be factored. So equation 2 could be rewritten v initial minus v final, v initial plus v final is equal to m v final minus v initial, v final plus v initial. And now we could divide that equation by equation 1 and get what? Well, these two terms die, and we get vi plus vf is equal to vf plus vi. Okay, now I want to rearrange that slightly because we have a mixture of initial and final conditions on both sides. So I'm going to put them back on their respective sides. And now I want somebody to describe in words what that means. Because with a verbal description, you'll hang on to it way better than with an algebraic description. Ooh. Yeah. She says that the relative velocity between the two objects remains the same. Yeah. She says maybe it's the relative. What do you think about that? Yeah, she agrees that. So the speed difference, imagine that both of those particles must be the torrential rain that's causing. All right, so both of these particles are moving to the right at the same speed. Okay, well, then this wouldn't be particularly informative, 0. And no collision happens, and 0. Let's say instead that the little particle is a sitting duck. So its initial velocity is 0. It's just sitting there, and it's being aggressed upon by the large particle. I mean, we have actors here. We could use them. Okay, so here is the whole drama for you. Okay, oh my. Okay, fine. So in that case, this is gone. And what's the relative speed? Well, one's at rest and the other one's coming in at v. So v is the relative speed. And then what is the meaning of this? So v final minus big V final would be the difference in the speeds as they go out. Yeah, so the relative speed is preserved. Anyone remember once upon a time we made some comment about coefficient of restitution? And do you remember what that was? No frickin' idea. Yeah, so in this case, the coefficient is 1 because the relative speed is the same after as it was before. And in general, it will be a little less or a lot less, or in a completely inelastic collision where they stick together, it will go to 0, and then the relative velocity after the collision is 0, and that's a coefficient of restitution of 0. So the ratio of the relative speeds is called the coefficient of restitution.